My name is Claudio Imbrenda, and I'm presenting this work analyzing cacheable traffic in ISP access networks for micro CDN applications via content-centric networking, which was done together with my two supervisors, Luca Muscariello and Dario Rossi. So this is the outline. Basically, first we will explain why we are doing this. Then we will introduce our monitoring infrastructure. What and where are we collecting and which data are we collecting, the statistics that we collected and the one that we calculated. Then we will show the trace-driven simulation that we did and the traffic characterization, and finally we'll draw the conclusions. So let's see the motivation. First of all, traffic is skyrocketing. This is not news. There's lots of web traffic, lots of video streaming. That's mostly from outside of the ISP, unpredictable, and most importantly, ISPs tend to invest more in the access network, which means that the backhaul is more loaded. So our proposal is to do this micro CDN, which means to cache at the very edge of the network. Of course, caching has benefits because you produce traffic, so of course it works. But one interesting thing is that most ICN proposal, information-centric networking proposals, they include caching as a primitive. So this study basically can serve as an enabler for that technology. Say, okay, it makes sense to do it. If you do it, you do have some advantages. It's not just something that you have and you will never use. Okay. First of all, HTTP analysis. We analyzed HTTP traffic, and in order to correctly analyze the HTTP traffic, especially for our purposes, you need to have an accurate analysis of the traffic, which means that you just need to request or maybe the reply and some timestamps. You need to have the to relate the reply to the correct request. You need to know the name of the object, the size of the object, including both the advertised size and the effective size, and in case the presence of e-tag and cookies. We need to know the sizes of the objects because we need to estimate the size of the caches. If you don't know the size of the objects, how can you estimate the size of the caches? So this simple diagram shows an HTTP transaction with a request and a reply. You can see the content length header is what I called advertised length. Is the length of the real object on the server, but the effective length or real length is the real amount of data transferred because maybe the client interrupted because the user was bored and interrupted, or there were some network problems and the connection broke. So in many cases it happens that the connection is broken and the real amount of data transfer is less than the advertised length, and this is important to have because we want to do the sizing with the real length. So of course there are tools that do collect HTTP traffic and do some kind of analysis, but we had to develop our own, which is called hacksaw. There are two tools that are mostly used in literature, TSTAT and BRO. TSTAT is fast and lightweight, more or less, and but it does not even correlate the request with the reply. So you just get a request and a reply, and you have to do the correlation yourself based on the timestamp, hopefully, if nothing breaks. So that's not really useful for our situation. Plus, it misses the size of many objects. And BRO is an intrusion detection system. It was not meant to be used like that. So of course it has some shortcomings, like it uses lots of memory and it's too slow. So this table shows an example of the performance of the three tools on a sample trace. It's a 1 hour pickup trace of mobile backhaul traffic on a peak hour with several thousands of users, and we can see that all the tools manage to fetch more or less all the requests. The memory usage is very low for TSTAT. It's very high for the other two tools, but it's still okay. I mean, this is doable. This is totally unacceptable because the trace is a 1 hour trace, and this is more than 2 hours. So if you need more than 2 hours to process a 1 hour trace, it's obvious that you cannot do it at line speed. And this is the amount of replies whose length is either 0 or missing. So you can see that tstat misses the lengths of many objects, whereas bro gets mostly the advertised length and misses the real length, whereas we catch all of them. So this is the reason why I needed to write the hacksaw tool. Now, where did we put our shiny tool? We put it there. That's lower, I mean, more to the edge than the edgemost router. This is the last router, and then there's no more routers. This is just optical switches basically. So we put our probe there. This is mostly fiber users, residential users, from April 18th to May 30th. It's more or less 1,000 hours. It's not many users in the end. There have been many studies with more users, but we intentionally did the study with only 1,500 users more or less, because that's our goal, is to measure the cacheability with a low amount of aggregation. Like we only have a handful of users, and we want to see if it still makes sense to cache. So this is where we put our probe. Okay, let's see what we got from the probe. First of all, what did we get from the software? We get timestamp of the packets, the MAC address of the client, which is a client ID basically, the IP addresses, the connection length, meaning the real size of the objects, and then the URL, the content length, and if present the E-tag. And we consider the URL and the E-tag as the content ID. The E-tag is a header that might be put into the reply headers by the server. It's basically a string, and the sole purpose is to identify different versions of the same object. Basically, like if there is a newer version of the same URL, it will have a different E-tag. That's the purpose of this, is exactly for caching purposes, so that you can you know if the copy in your cache is new or not. The same URL with the same E-tag means the same object, and the same URL with different E-tag means a different object. That's why we consider the concatenation of URL plus E-tag as a content ID. The E-tag is not present. When it's not present, we didn't put it. We just consider a URL, or actually a hash of that. But, yeah. So what statistics did we compute from that? We computed these three key statistics: request cacheability, traffic reduction, and visual cache size. They all refer to specific time intervals. So the cacheability, for example, is the percentage of repeated requests for the same object in the given time interval. If an object is requested only once in a time interval, we don't consider it as cacheable because it was requested only once. Doesn't make sense to cache it. If it's requested at least twice, then it makes sense to cache it, because by caching it, you can save the subsequent request for the same object. So that's what we mean with cacheable requests. The traffic reduction is a similar metric, but with a slight twist. It's the percentage of traffic that could be cached by a perfect Oracle kind of cache. We assume prefetching here, so we assume that all cacheable traffic is prefetched. This is a very optimistic scenario, but it does give us a clear upper bound on the amount of traffic that can be reduced. I mean, that's really the upper bound. We cannot save more than that. The virtual cache size is just the size of all the cacheable objects observed. So basically, assuming we have this perfect Oracle kind of cache, what is the smallest size that this cache should have in order to cache all the cacheable objects, basically? This is a lower bound of the size of the cache, meaning that if we have less than that, there's no way we can cache all the cacheable objects. Because of course a real cache will perform worse, but we will see that. So first of all, we considered 3 different scenarios, and we saw how these statistics look like in there. So first is just caching at the OLT, which means our vantage point, the optical switch. Then we see what happens if we only cache at the clients. Let's suppose that every client has a cache in the home router, and see how that performs. And then we see, okay, what's the performance, and now what are the statistics here at the vantage point after the caches at the clients did their job. So these are the results for the cacheability at the vantage point. The cacheability is over 40%. The traffic reduction, this is not shown here, is around 35%. This actually is the cacheability both on daily and hourly time slots. Of course, hourly is lower because there's the time slots are smaller, so many more objects are considered non-cacheable. Interesting is that the virtual cache size is only around 100 gigabytes, which means that it can be done in a line card with the current technology already. So it's nothing, no miracles are needed. What is interesting here is caching at the user. We see that the cacheability is lower, but it's still quite high. The virtual cache size here is only 100 megabytes, which is very, very low. I have to say this is an average of over all the users. So of course the variance is very, very high, but still this will 100 megabyte cache will be beneficial for many, many users. And 100 megabytes, it's feasible right now with the current technology. I mean, the current boxes that people have in their homes, they already have that much memory, or maybe even more. And finally, let's see what happens at the vantage point after the clients after the caches at the clients did their job. We still see that there's a more or less 20% cacheability. The traffic reduction is also 20%. The virtual cache size instead is still around 100 gigabytes. It's actually a little bit lower, but it's still around that value because big objects maybe are requested by more than one client, and in that case you need to cache it at the vantage point, and that takes space. So it's still feasible, of course, with the current technology. Also, this level of cache would basically catch all those users, all those outliers that would not be cached in the 100 megabytes, because, as I said, there was a high variance on the amount of cacheability and on the basic answer on the size of the virtual cache. This level would still be needed. So probably with a real cache, this would be probably higher. Okay, so this is a summary of the results we saw before. We can see that the virtual cache size is 100 gigabytes still doable, and 100 megabyte for the cache at the user, which is really good. Now we did some trace-driven simulations from this. We now consider real LRU cache because yes, all these statistics are nice and everything, but how does a real cache perform in that situation? Also, we wanted to assess temporal locality of content. So we consider we simulated an LRU cache. The important thing is that it's chunked based, meaning that it will only cache the part of the objects that are really requested. So if an object is huge but they only request a small part, only that small part is cached. Okay, first of all, at the vantage point, we put the cache only at the vantage point and see what happens. we tried 4 different cache sizes from 1 GB to 1 TB. 100 was the ideal perfect kind of cache. Of course, we need more. Of course, as expected, the real performance is lower than the theoretical values. 100 gigabytes does not reach the over 40% we saw before, but that's expected because this is a real cache, it's not perfect. The 1 terabyte cache, though, it does reach 42% hit ratio. This is the saved traffic. It's significantly lower, also because this is a real cache, and also because we are not prefetching anything. So of course we are not able to do that well as a traffic reduction metric. But still, it's a good value. It's over 20% for the 1 terabyte cache, sometimes 25%. What we see here is, this is very nice, is that the cacheability and the traffic reduction metrics, they do give, and the virtual cache actually also, they do give a good estimation of the real values that we see here, and they are significantly easier to calculate. This is a real LRU working on the data. It takes a lot of time and effort, whereas the virtual cache size and the traffic reduction and cacheability values, they are just computed like it's literally just a division. It's very simple to compute. So here we see that the numbers are really nice, and that it's not that far away from what we saw with the cacheability and traffic reduction values. So now we want to actually to assess, as I said, the temporal locality and see how that impacts the performance of the cache. So we consider 1 hour and 1 day time slots, and we basically shuffled all the requests uniformly, randomly, and we saw that yes, small caches suffer, obviously. So this is the 1 gigabyte cache. Without shuffling is 19%. With shuffling is only 10%. It's interesting to see that the 100 gigabyte cache is not affected by the 1 hour shuffling, but is affected by the 1 day shuffling, and the 1 terabyte is basically oversized because it's never affected. This is true for the hit ratio and for the traffic reduction. We do see that the 1 gigabyte cache is totally useless when shuffling over 1 day, and it does something when there is no shuffling, which means that IRM models are too conservative, basically. If you assume that your requests are arriving with an IRM model, this is not representative. And if you decide that a cache is useless because with IRM it would not yield any gains, then maybe that's not the right approach to follow, because you can actually get some gains from that. So temporal locality does have an impact. So some traffic characterization now. First, we try to fit the popularity of the content. This is the content popularity rank by normalized popularity. We use a trimodal distribution, viable, zip viable. This is needed because the alpha of the zip is less than 1, which means that the support is finite, but the confidence interval to estimate the size of the catalog is unbounded. And you need that to size the cache, because the hit ratio is proportional to the cache size of an active catalog. So you need to know the size of the active catalog, and if you cannot estimate it properly, then you estimate wrong sizes for the caches. So viable instead does not have problems when the shape parameter is less than 1. So this trimodal does fit the distribution nicely, and passes the chi-square goodness of fit. So it works and can be used for a model. Okay, so next up, time correlation. As we show the real-time correlation, this graph in particular shows the average time needed to reach a given percentile of the asymptotic cacheability and traffic reduction. We can see that within a few hours, you reach already 75% of the asymptotic cacheability and traffic reduction values. We consider different intervals from, as I said, 1 hour to over 96 hours, which is our asymptotic value basically, and can be seen that 75% is reached already in a few hours. So we wondered, what is the refresh rate of the active catalog? We considered 1 hour time slots, and we basically ask ourselves when and how much of the content in each time slot will be requested again. For this, we used Jacob coefficient, which basically is the cardinality of the intersection over the cardinality of the union of two sets, considering a set of different objects of seen, basically the catalog seen in two time slots. So this gives a ratio of how much of the catalog in the two time slots is the same. And then basically we did some kind of autocorrelation function using this, and we can see here how that looks like. So this is the distance between the first time slot observed. This is an average over all time slots of the coefficient calculated on that time slot and the time slot at distance d. So we can see that even at distance 1, so in average, the similarity between every time slot and the next one is only 4%, actually less than 4%. There is a weak 24 hours periodicity, which means that people tend to look at the same content more or less at the same time of the day, but it's very weak. It's like 1%, 0.5%. So we can actually see that there's not much correlation between the catalogs, which is very interesting. So the content changes very, very quickly. So what we can conclude is first that IRM zip models are inadequate to model this kind of traffic, and time correlation is more important. Caching, even in the access network, does yield real traffic savings, and from this point of view, ICN solutions with native caching will provide real benefits. You don't have to do anything, you just put the box and it just works, and it will give benefits. Small caches can provide real benefits. Small caches can potentially reduce the load on the backhaul up to like 35%. And this is something that hindered our efforts actually. HTTPS did not only prevent us from seeing the traffic, but it will also prevent caching from happening in this scenario. You cannot do transparent caching if you have an HTTPS tunnel. So far we only saw that more or less 15% of the traffic was HTTPS, but it's growing and quickly. Also from this point of view, ICN solutions are good because they have many of the advantages of HTTPS, namely some security aspects and verification aspects, but they don't hinder caching. So that would be beneficial, or otherwise we would need some kind of new encryption-aware version of HTTP. Finally, some future work. I plan to improve the tool to get it more accurate and to have a smaller memory footprint. Then we want to have more probes, both inside the network in different places, or a different, different places, but meaning like here in France or all over Europe, and different points, like meaning close to the access or further away from the access, to see how it works. That's all.
I have a question.
Okay.
Do you think, a you say like the use of, you talk about the use of CCN kind of networks, and I'm thinking if caching would be useful also if CCN networks get to the home, I mean to the object in the Internet of Things approach. If you have like NDN sensors, I mean CCN-based sensors, and the caching inside the home, if it would be relevant or not. I mean, if you
probably that would not be useful. I mean, it doesn't make sense to cache the output of sensors inside your own home. I mean,
for example, you don't need to query the sensor several times. I mean, you query only one and then.
Yeah, well, maybe, but I mean, our goal here was to measure the impact on the backhaul. So from that point of view, I don't think the traffic of the sensors inside the home will impact the access network or the backhaul of an ISP in any significant way. So, yeah. I mean, if many people are suddenly interested in the temperature in your apartment, maybe, but
only for the home.
Yeah, maybe. I mean,
load inside the home.
Sure, but yeah.
Because I mean, I was shocked by the amount of traffic that is cacheable from one home only. I mean,
yeah.
Almost 30%. Is kind of big.
Yeah, I know. Yeah, but that's traffic towards outside. I mean, it's the user requesting content from outside that needs to be brought in. This is not.
But most of IoT solutions today are sending all the information to the cloud and then.
Yes, but with CCN you don't need to have that. Because if your sensor has a name, you can query your name anywhere in the network. You don't need to go in the cloud. But, yeah. So I don't know how much traffic does the sensor generate anyway.
Just to make sure I understand the assumption. So when I store a content in my box, the ONT, can I also serve other boxes?
No. Here all our measures don't assume any box-to-box communication here.
Why? You just consider serving at OLT or at the ONT?
Yeah, we consider only cache. We didn't consider that. Many ICN solutions only do on-path caching, for example, which would be this kind of solution, for example. Off-path caching is more tricky and is not built in already in ICN solutions, whereas on-path caching is built in many, almost any ICN proposals we saw. So that was the obvious thing to do to see how that performs. Then off-path caching is of course being researched also for CCN, but we didn't consider it for this study.
So how do you explain the observation that you made in slide 28 or something? On the catalog, the fact that it changed a lot from one to the other period, or you can cache quite a large amount. So
yes, all of our cacheability measures were over a rather small time slot, meaning either 1 hour or 1 day, mostly 1 day. The good values were basically 1 day. And also the LRU simulation was performed on 1 day time slots, meaning that after cacheability over one hour time slot or 1 day time slot means that if there is a new content in the next time slot, we don't see it, we don't consider it as cacheable. So
because you took the assumption in your first slide, you said that we assume we have an oracle to know what we have to cache, right?
That's for the cacheability measures, yeah. And for the traffic reduction mostly, yes. I'm not sure I understand the question.
Well, you can talk about that.
Okay.